On the morning of June 6, 1944, a 19-year-old private from Akron, Ohio, waded ashore at Omaha Beach with a rifle he had never truly cleaned. He had trained with it for 8 weeks at Camp Blanding, Florida, fired it at paper targets in the Carolina Piedmont, and dragged it through the mud of the English countryside for 4 months waiting for the invasion. The rifle was the M1 Garand. It weighed 9.5 pounds. Its stock was American walnut. Its barrel was machined from chrome molybdenum steel. And its trigger group housing, the curved, unassuming piece that held the entire firing mechanism together, was made of a dark brown thermosetting plastic called Bakelite. He did not think about the housing. No soldier did. That was precisely the point. 3 years earlier, the United States Army Ordnance Department had made a decision so quiet it never appeared in a press release, never earned a general a medal, and never made the front page of any newspaper. Facing a production bottleneck in small arms manufacturing, the department's engineers had approved the substitution of walnut wood components on the M1 Garand with injection-molded synthetic parts where tolerance is permitted. The decision was not celebrated. Some officers protested. A rifle was supposed to be made of steel and wood. That was how it had always been done. The German infantry officer, who would later write his memoirs in a Bavarian farmhouse after the war, described finding a captured M1 Garand in the bocage of Normandy. He turned it over in his hands. He pressed the trigger group housing with his thumb. He tapped it on a stone wall. He wrote that he immediately called 2 of his engineers over to look at it. None of them could agree on what the material was. They had never encountered a weapon built this way. The plastic was uniform. It was precise. It did not crack. It did not warp in the wet Norman summer. It weighed almost nothing. And it had been made, they eventually concluded, not by a craftsman, but by a machine. In enormous quantities, to tolerances that should have been impossible for a non-metal material. This is the story of how plastic changed modern warfare. Not explosives, not radar, not the atomic bomb. A synthetic resin discovered by a Belgian-American chemist in a home laboratory in Yonkers, New York in 1907. What it did to the Second World War and why Germany could never follow where it led is a story about systems, culture, and the distance between knowing a thing and being able to build it at scale. The man in the laboratory on Snyder Avenue. Leo Baekeland was 43 years old when he mixed phenol and formaldehyde under controlled heat and pressure in a laboratory vessel he called the Bakelizer, and produced a substance that did not exist in nature. He had already made one fortune, selling the rights to Velox photographic paper to George Eastman of Kodak for a sum that allowed him to retire and pursue pure research. He chose not to retire. He went back to the laboratory. What Bakeland had created was the world's first fully synthetic plastic. A hard, heat-resistant, non-conductive material that could be molded into any shape and, once set, held that shape permanently. It did not melt in heat. It did not conduct electricity. It did not absorb water. It could be made opaque or translucent, black or brown or red. It could be machined like metal, sanded like wood, and produced in quantities that neither metal nor wood could match. By 1910, the Bakelite company was selling to electrical manufacturers, telephone handsets, radio casings, distributor caps for automobile ignitions, insulators for power lines. Bakelite went wherever heat and electricity coexisted and where traditional materials failed. The trade press called it the material of 1,000 uses. Bakeland himself was more measured. He told a journalist in 1924 that the material's greatest application had not yet been discovered. He was right. He would not live to see it. In 1929, Bakeland sold the Bakelite company to Union Carbide. The patents were absorbed into a larger corporate structure. The research continued. By the mid-1930s, American chemical engineers had developed injection molding techniques that could produce complex Bakelite components, parts with internal threads, cavities, and interlocking features at cycle times of under 30 seconds per piece. A single injection press running 2 shifts could produce 10,000 identical components per day. Each one would pass a gauge test. Each one would be interchangeable with every other.
The American system of manufacture, the gauge tradition that had begun with John Hall's breech-loading rifle at Harper's Ferry in 1819, had found a new material. What Hall had done for steel, the injection mold would do for synthetics. The question, as it had always been, was whether industry had the discipline to hold the tolerances.
Springfield writ small. The M1 Garand had been adopted by the United States Army in 1936 after a decade of trials, setbacks, and political fights that nearly killed it twice. Its designer, John Cantius Garand, a quiet Canadian-born engineer who worked at Springfield Armory for 33 years without ever seeking a patent royalty for his invention, had built the rifle around the principle that every single component had to be manufacturable to tolerances tight enough for field-level interchangeability. A soldier in the Philippines should be able to disassemble his M1, borrow a trigger group from a dead man's rifle on Bataan, and keep fighting. Garand designed toward that requirement from the first drawing. When war came in December 1941, Springfield Armory was already producing M1s at scale. Winchester Repeating Arms had a second production contract. The challenge was not design. Garand had solved the design. The challenge was volume. The Army needed hundreds of thousands of rifles, and the walnut stocks were the first bottleneck. Walnut had to be seasoned. It moved with humidity. It required hand fitting at the barrel channel. Every stock was slightly different from every other stock. The Ordnance Department's solution came from a weapons engineer named Rene Studler, who had spent years studying European small arms and returned with the conviction that American production methods were being underused. Studler pushed the substitution of synthetic materials wherever the engineering permitted it. The trigger housing was the first major component approved for Bakelite production. The process was straightforward. A steel mold machined to exact specifications, polymer resin injected under pressure, cycle time 38 seconds, part ejected, dropped into a bin, gauged by an inspector. Pass or fail. No adjustment, no file, no hand fitting. The inspector's gauge was a go, no-go fixture, a hardened steel tool that either accepted a part or rejected it in a single motion. There was no middle ground. A part that almost passed was a part that failed. It went into the scrap bin and was counted against the supplier's reject rate. Too many rejects, and the contract was reviewed. Studler had learned this from William Knudsen, who had learned it from Henry Ford, who had learned it from the men of Springfield and Harper's Ferry. The chain of transmission was unbroken. By 1943, 12 separate manufacturers were producing synthetic components for the M1 and its variants. The trigger housing, the handguard liner, the gas cylinder components, parts that had once required skilled machinists, were being produced by workers who had been trained in weeks, not years. The knowledge was in the mold and the gauge, not in the hands of the man running the press. The German dilemma. Germany was not ignorant of synthetic materials. German chemistry was in many respects the finest in the world. BASF, Bayer, IG Farben, these were not provincial operations. German researchers had pioneered synthetic dyes, synthetic rubber, synthetic gasoline. The Kaiser Wilhelm Institute produced Nobel laureates in chemistry, the way Henry Ford produced automobiles. If Raw led the world in polymer applications. But Germany's weapons industry had a structural problem that its chemical industry could not solve. The Wehrmacht small arms, the Karabiner 98K, the MG42, the MP40, were manufactured in a culture that prized the Facharbeiter, the master craftsman, above the machine. A stock blank for the K98K was rough-shaped by machine, then finished by a man with a draw knife, a scraper, and a set of calipers. Two stocks from the same factory on the same day might differ by half a millimeter at the barrel channel. A half millimeter was within the craftsman's tolerance. It was not within the gauges.
When the Wehrmacht's Ordnance Bureau attempted to introduce synthetic components in 1942, it encountered a manufacturing system that had no tradition of running to the tolerances injection molding required. A Bakelite trigger housing that came out 0.02 of a millimeter oversize from an improperly maintained mold would not fit the receiver on a rifle whose receiver had been hand-fitted by an artisan working to a slightly different standard. The parts were not interchangeable because the system that produced them had never made interchangeability its foundational discipline. The German solution was the same solution German industry always reached for: the skilled worker. A man with a file could make any part fit any other part. A man with a file could correct the mold's error, the machine's drift, the supplier's deviation. But the man with the file was a bottleneck. He worked one part at a time. He could not be replicated by decree. He had spent 5 years as an apprentice, 3 more as a journeyman. He was irreplaceable. And in a total war, irreplaceable things become fatal weaknesses. By 1944, the Wehrmacht was fielding a weapon that illustrated the contradiction perfectly. The Sturmgewehr 44, the world's first assault rifle, a design so advanced that it influenced every infantry weapon developed in the following 50 years, used pressed steel stampings and synthetic components specifically to ease mass production. The concept was correct, but the factories producing it had no centralized tolerance authority. Subcontractors across 4 countries were making components to their own interpretations of the specifications. Assembly workers at the final plants spent hours fitting parts that should have dropped together in seconds. Production targets were missed every quarter. In the last year of the war, the Wehrmacht received perhaps a third of the Sturmgewehre it had been promised. What the gauge teaches. To understand why the gauge tradition never crossed the Atlantic in the way it crossed from Springfield to the Crystal Palace in 1851, you have to understand what the gauge actually demands of an industrial culture. A gauge does not ask whether a part is good enough. It asks whether a part meets the specification exactly. These are not the same question. The craftsman answers the first question with pride, experience, and judgment. The gauge answers the second question with physics. The craftsman can be argued with. The gauge cannot. American industry had spent a century and a half building the cultural and institutional infrastructure required to live with the gauge. It had the Springfield Armory tradition of metrological discipline going back to John Hall. It had the Detroit automotive industry's experience with production tolerances measured in 10,000ths of an inch. It had William Knudsen's practice of confiscating files and throwing out parts. It had the contractual language that made reject rates a condition of payment. Every one of these things was an institutional habit, built slowly, broken and rebuilt, tested against the market's demand for cheap and fast, and ultimately surviving because the alternative, hand-fitting, could not scale. Germany had the chemistry, it had the physics, it had engineers who understood in the abstract what injection molding required. What it did not have was the century and a half.
You cannot mandate the gauge tradition into existence by wartime decree. You cannot train an industrial culture out of its habits in 4 years of total war. The habits are in the contracts, the apprenticeship structures, the management expectations, the supplier relationships, the inspection protocols. They are in everything. A report filed by the United States Strategic Bombing Survey in 1945, examining captured German small arms facilities, noted with clinical precision that German factories producing synthetic weapon components consistently showed interfactory variation in critical dimensions of 2 to 4 times the tolerance specified on the engineering drawing. The survey's authors, American industrial engineers, men who had run production plants, described the finding in terms that carried an unmistakable subtext of disbelief. They had expected better from the country of Krupp and Zeiss. What they found was a manufacturing system that had grafted new materials onto old methods and was paying for the mismatch with every shift.
The arsenal at dawn. The scale of what American synthetic materials production achieved in the Second World War has never been fully absorbed into the popular history of the conflict. Between 1941 and 1945, American factories produced more than 12.5 million M1 Garands, M1 carbines, and associated weapons with synthetic components. The injection molding plants that supplied them ran 24 hours a day, 7 days a week, with shift workers, housewives from Cincinnati, men too old for the draft from Akron, students from night school in Detroit, operating presses with a few hours of training. The parts they made were identical, not approximately identical, not within a craftsman's judgment of identical. They were metrologically identical, part to part, batch to batch, factory to factory, year to year. A trigger housing made in Cincinnati in January 1942 would fit a receiver made in New Haven in October 1944, with the same clearance, the same function, the same reliability. This was not magic. It was gauges and discipline and the willingness to throw the part away if it did not pass. The logistical consequence was decisive. American ordnance battalions in the field could maintain weapons not because they had skilled gunsmiths at every forward depot. They did not, but because the parts were interchangeable. A broken trigger housing was a 2-minute fix. The part came out of a box, it dropped in, the rifle went back into the soldier's hands. The German armorer in the same position faced a different reality. Parts for the K98K from different production batches might require fitting. Parts for the MG42 from different factories might require adjustment. Every repair was a negotiation between the part and the weapon, mediated by the armorer's skill and his file. There is a document in the National Archives, a report filed by an ordnance company commander in the 3rd Army sector in January 1945, that describes a forward repair depot processing captured German weapons alongside American ones. The American weapons were being returned to service at a rate of roughly 4 per man-hour. The German weapons, captured in the Ardennes fighting, were taking an average of 6 to 9 man-hours each because the replacement parts, where they could be found at all, required fitting. The commander did not theorize about why. He just recorded the numbers. The numbers told the story. The inheritance nobody claimed. In 1946, a team of American engineers from the Ordnance Department visited the Walther factory in Zella-Mehlis, which had spent the war producing the P-38 pistol. They found machinery that was, in many cases, newer and more sophisticated than equivalent American equipment. They found engineering drawings of extraordinary precision. They found chemists who understood polymer materials at a theoretical level that matched or exceeded anything their American counterparts could demonstrate. What they did not find was a gauge calibration system with traceability to a national standard,
What they did not find was a supplier qualification program that imposed and enforced tolerance requirements. What they did not find was any mechanism for systematically rejecting parts that made specification without an override option available to senior craftsmen. The Ordnance Team's report, declassified in 1958 and studied by almost no one, concluded with a sentence that deserves to be better known. It read, in summary, "The Germans built extraordinary weapons, and then built them again, slightly differently, every time. America built ordinary weapons and built them the same way, correctly, millions of times." The war was decided by the second sentence. Leo Baekeland died in 1944, the year the war turned irrevocably against Germany. He had spent his last years largely retired, watching the material he had discovered in Yonkers spread through every industrial economy on Earth. He did not see what his invention did at Omaha Beach, or in the hands of the ordnance battalions fighting through France, or in the repair depots that kept 12 million American rifles functioning across 5 years of global war. He left behind no memoirs. His laboratory notes were meticulous but technical. He was a chemist, not a military historian.
But in a sense, the connection is direct. Bakeland created a material that could be molded to exact specifications and reproduced without limit. American industrial culture created the system that could hold those specifications and enforce them under the pressure of total war. Germany had the first ingredient and not the second. That asymmetry played out across millions of parts in thousands of factories over 4 years of production is why the war ended the way it did. The part that did not need you. There is a photograph in the collection of the National World War II Museum in New Orleans. It shows a supply sergeant somewhere in Belgium in the winter of 1944, kneeling beside an open crate of M1 Garand stocks. The stocks are made of a laminated polymer composite, a later war substitute developed when walnut supplies tightened further. The sergeant is holding one up to the light. He is not inspecting it for fit. He is not measuring it. He is looking at it the way a man looks at something that works so reliably, he has stopped thinking about whether it will work. Somewhere in the same winter, a German armorer in a Wehrmacht depot outside Cologne was working by lamplight on a stack of K98K rifles that had come in from the Hürtgen forest. He had replacement parts. Some of them fit. Some of them required work. A few strokes of a file here, a slight reaming of a hole there. The kind of adjustment that took minutes and that a skilled man could do in his sleep. He had been doing it since 1940. He would do it until there were no more rifles to fix. The distance between those two men, the sergeant with the crate and the armorer with the file, was not a distance of skill or intelligence or even resources. It was a distance of systems. One system had spent 140 years learning that the part must not need the man. The other system had spent the same 140 years believing that the man was the solution to every problem the part presented. Both beliefs produced extraordinary things. Only one of them produced enough extraordinary things, consistently enough, to win a war. The plastic handle on the M1 Garand's trigger housing weighed less than 30 grams. It cost a few cents to produce at wartime contract prices. It required no skilled labor to make, no fitting to install, no adjustment in the field. To the soldier who carried it from Normandy to the Rhine, it was simply part of the rifle, invisible, unremarkable, utterly reliable. To the system that produced it, it was the end point of a journey that had begun in a federal armory in West Virginia in 1819, traveled to the Crystal Palace in London in 1851,
crossed back to Europe and failed to take root, returned to Detroit and Akron and Cincinnati, and finally arrived in the hands of 19-year-olds wading through the surf of occupied France as the answer to a question that had taken a century and a half to fully formulate. The question was not, how do you build a weapon? Every industrial nation had answered that question. The question was, how do you build 10 million of the same weapon so that every one of them, from the first to the 10 millionth, is the same weapon? The Panther, on paper, was the finest tank of the war. The Sturmgewehr 44, on paper, was the finest infantry weapon. The K98K, machined by master craftsmen in the finest small arms factories in Europe, was a weapon of extraordinary quality. None of it mattered. What mattered was the gauge. What mattered was the 30-gram piece of brown Bakelite that dropped into its seat without a file, without a caliper, without a craftsman's judgment, because the mold that made it had been machined to specification. The press that ran it had been calibrated that morning. The inspector who passed it had a gauge that traced back to a national standard. And the culture that produced all of this had been building toward this moment, since John Hall looked at a musket lock in 1799 and asked why it could not be made the same way every time by anyone. America had been answering that question for almost 150 years. The Bakelite handle was simply the latest answer. Germany never asked it at all.